All right, so we are at the final leg of dynamics. It's been quite a journey. It's been very interesting, but now we're with the last thing, which we're looking at the kinetics of rigid bodies. And the last lectures are going to be dedicated to the kinetics. Kinetics, same thing as what we did when we looked at the kinetics of particles, but now we have to consider rotation. Oddly enough, not in today's lecture, and not in the first couple of problems that we're going to be doing. But that's pretty much about it. So let's get into it. So looking at, oh, and again, public service announcement, homework 7 due today. Make sure you guys get that in. I know I've been terrible at grading homeworks, probably the worst I've ever been any semester. But with the exam grades, you guys have a good idea of where your grades are at. Just make sure you get the homeworks in because they are 20% of your grade, and I will be grading them. You'll basically see either the week before finals week or finals week, you'll see quickly all your homework grades coming in. So make sure you keep getting the homeworks in. All right. Okay, so let's get into it. Rigid body kinetics, right? So who remembers particle kinetics? So what was Newton's, so today, we're basically looking at Newton's second law, but with rigid bodies. So recap from looking at particle kinetics. Right? What do forces do when we're looking at dynamics? They cause motion, right? So they cause translation motion. Right? And how do we express that in an equation, or equations rather? Guys, if you can't tell me the Newton's second law equation right now, I'm just, we're not going to produce anything. Yeah.
F equals ma.
All right, thank you. So sum of all forces acting on a body is equal to the mass times the acceleration that's acting on the body, right? And on all vector directions. Now, long time ago, when we first started dynamics, which seems like super long ago, we'd also said that moments cause rotation, right? And that's what we're going to be looking into. So moments cause rotational motion. All right, and the moment can be found about an axis passing through any random point, right? But to make lives easy, we usually like to consider the moments about, well, it depends. It's very problem dependent, but in a general sense, we like to take the moments about the mass center, the center of gravity, or the centroid, which for our intents and purposes is the same thing, right? But some people will tell you that centroids and mass centers are not the same. They might be right, but for us, we're going to consider this to be the same, right? So the sum of all moments acting on a body about any point is equal to, well, it's about its center of gravity here, is equal to a quantity called I, and we're going to call it m, subscript g, times the angular acceleration that's acting on your body. And this will be as a vector, as we know. All right, so the question is, what is this I? And this I is defined as the mass moment of inertia. All right, so this is called the mass moment of inertia. Again, depending on who you're speaking to, some people might call it rotational inertia. Some people might call it the first moment of inertia. Some people might call it the angular mass, right? I think from my point of view, I guess rotational inertia is the most accurate way to do it, right? Because it describes how easy or difficult it's going to be to rotate a body, all right? And the way that we define it is, right, remember, whenever we're looking at rotation, you always need an axis, right? So we draw the axis out. Dot A, A prime like that, right? And then, so this is the axis about which your rotation is happening, right? So then we have any random rigid body, right? And let's say that this rigid body is broken up into infinitesimally small volumes that have the mass dm, right? And that the shortest distance, or another way to say it, the perpendicular distance to the axis of rotation, whoops, right? Let's say that that distance is equal to r, all right? And just to drive home the point, so the body is rotating about this axis. All right, so the definition of the mass moment of inertia, the rotational inertia, is you always want to say what point or what axis you're finding out your moment of inertia about, right? So here you have I about the axis A prime, right? And that is defined as the integral of all of the masses, so the whole mass of the body times r squared times dm. So you're integrating the squared of the distance times the infinitesimally small mass over the whole mass of the body. All right, important things to remember. Right, the mass of a body for us, right, for what we've gone through in dynamics, it remains fixed, right? It does not change. So that mass is absolute. So whenever you're working with Newton's second law and you're saying F equals ma, this quantity here, the mass, for all intents and purposes, remains the same, right? We're good. It does not change. But the mass moment of inertia, which goes into the second expression, where rotation is coming into the picture, right, is relative. And what is it relative to? It depends upon whatever axis about which you're considering the rotation to happen. Right? Why does it depend on the axis? Because the axis is going to change what your distance r that you're integrating over to find out what your rotational inertia is going to be. All right, you guys would have seen in statics, you would have seen second moment of inertia, area moment of inertia, right? Different. This is the first, this is the mass moment of inertia. All right, so the formulas are different. Again, we're going to go through and we're going to do a bunch of derivations today, but look to the back of your textbook for the moments of inertia of standard bodies, right? And then you use, it's the same thing as area moment of inertia. You just have to use parallel axis theorem and things like that to figure out what the moment of inertia is going to be for the problems that you're looking at. All right, similar to the area moment of inertia, you do also have the radius of gyration, right, which is defined as a distance k, and that's just the square root of whatever your rotational inertia is divided by the mass m. Or you can say that IA prime is just equal to mk squared, like that. All right, you guys have any questions? All right, as we said, with your area moment of inertia, the same kind of principles apply. So you have the parallel axis theorem. All right, so parallel axis theorem, say you've got your rigid body like that. You've got an axis which passes through its mass center G. So let's say that this axis is like that. Let's call this axis A prime, and then let's have another axis parallel to that axis, right? Let's call it B prime, like that, whereby the perpendicular distance between the two axes is D, right? So this is your perpendicular distance between two parallel axes, right? So just to write out what everything is, whenever we're talking about G going forward, guys, capital G, we always mean it's the mass center, right? So G is mass center, and IG about A prime is assumed to be known, right? This is what you find out from the back of the book, or you derive it, right? You can find out what your mass moment of inertia about an axis passing through the mass center is going to be. Typically, it's easy for regular shapes, right? So what that means is that the moment of inertia about a parallel axis BB prime. All right, yeah, that's the other thing to know, that this axis is parallel to that axis, right? So I BB prime is equal to IG about that A prime, the parallel axis there, plus the mass times the distance squared. So basically, the exact same formula that we had for the, well, similar, I shouldn't say same, for the area moment of inertia. All right, now we're going to derive it for the two simplest shapes, that the most common shapes that we're going to be getting in, looking into, which are going to be discs and rods. Yeah, a uniform rod and a uniform disc. All right, are we good with this? Can I move on to the next page?
Yeah.
Ooh, was that Mr. Stroud? Did you see my email? Yesterday I sent you an email. We can talk about
okay.
it.
Yeah, I'll check it.
Yeah, all right. All right. Okay, so next page. So we have examples. So we have mass, moment of inertia. The first super common shape that we look at is a uniform tin disk of mass m and radius r. All right, so what we have is, let's see, so we have, I'm going to do a top view, I'm going to do a kind of a side / isometric view. All right, so we have that, and then we've got all right, so uniform disk. So we know that the center is G, you know that the radius is R, right? And we're trying to find out, whoops, the rotation about a z-axis that is perpendicular to the plane of the disk, right? So we're rotating it like that. And we're also told that the thickness is equal to t, right? So the xy plane is on the disk, and the z-axis is coming out, and that's the one that we're finding the moment of inertia about, right? So the task at hand is to find IG about the z-axis. All right. Experts at statics, what do we do to figure this out? Anyone has any ideas?
We wouldn't take the moment, would we?
No, no. You're literally going, what you're going to do is you're going to use this expression here. You're basically going to do r squared dm and integrate it over the whole volume about G. Calculus / statics. Did you guys do derivations of area? I'm sure you did derivations of area moments of inertia. How do
In
we?
static?
Yeah, in statics.
We didn't do much of that.
Okay. Well, think of calculus, right? Whenever you're doing integrations and doing it over whole bodies, how do you approach the problem? What's the thing that you do?
I don't know. You need to know your bounds.
Yeah. So the bound is that you're going from radius 0 to radius r, right? Good, good. Thinking in the right direction. Basically, the trick is that you need to find out what dm is. R squared can be integrated from 0 to capital R because that's given to you in the problem, right? And the trick is just finding out what dm is, right? So the way that you do this is, and you guys should have seen this in calculus, you break up your disk into, wow, terrible drawing, into really thin slivers. Right? So the distance of the sliver, let's say small r, and the width or the thickness of the sliver is dr. Right? So for this really thin sliver, I can say that dm is just equal to whatever the density of the body is, uniform density, because we're looking at uniform rigid bodies, times the differential volume of that, right? So now to find the differential volume, what I need to do is I need to find out what the volume is in terms of things that are given to me, right? So how can I find out the volume of this thin sliver?
This is of a thin disk, right?
Yeah, in a thin disk with a thickness T, right, at a distance R, with this thin sliver, with a distance, with a thickness of dr, what's the volume going to be?
Pi r squared times t.
Ooh, almost. Pi r squared times t would give you the volume of that guy. Oh no! Oh no! Oh no! It's gonna crash on me.
You just subtract that off the same equation for the.
Yeah. All right, guys. You gotta give me a second. So pi r squared and then pi plus d. But there's an easier way to do it.
It's r drt, right?
R drt. Nope, it's not. You're getting there. You're getting there. All right, guys. Take 2 minutes. Think about it. I need to recover my PowerPoint, which is going to be bad.
Is it r minus dr?
No. Think about opening that sliver up into a rectangle, and then you'll be able to figure it out.
Oh, so
it's the area.
Exactly. It's the area times t. And the area is just going to be 2 pi r times dr, right? Because the length of it, that little rectangle, is going to be 2 pi r. The height is dr. So 2 pi r times dr is equal to the area 2 pi r times dr times the thickness T, volume. You know what? I'm just going to where options, save,
Do you use PowerPoint to do all of your lectures?
yeah, terrible decision. But it's the best that I can, it's better than, are you in one of Dr. Eaton's lectures? He uses that online tool, right? I don't like that one as much.
Have you tried OneNote so you don't have to keep making new slides?
Yeah, I guess that's no, I haven't tried OneNote. All files. All right, so now I want to go there. Hey, not bad. File, save as, browse. Come on. Save your document. You guys get to see my super awesome, ergo terrible organization. Where do you spring there? Lectures, kinetics. Oh, there we go. What? All right. So we have that, right? And you know that thickness is going to be dr, right? So the trick when you're integrating stuff over a whole volume is that you've got to find out what your differential is going to be that you're integrating over and what your distance is, and then how you relate that to your problem, right? So yeah, we've said that dm is going to equal the density times the differential volume, and the differential volume, as we just said, is just going to be, imagine you take this little thin sliver and you open it up, right? The length of that sliver is 2 pi r, and the height is dr. So that gives you the area, and the thickness is T. Is that clear, guys?
Yeah.
So therefore, the moment of inertia, the rotational inertia, by the way, guys, whenever I say moment of inertia in dynamics, always talking about the mass moment of inertia, the first moment, the rotational inertia, all right? I hope that doesn't confuse you guys. We're not looking at J's, we're looking at I's. All right, so the moment of inertia is that's the definition, right? But now we've changed this around, right? We've said that we have r squared times rho times 2 pi r dr t. And the only thing, the differential that you have that you're going to be integrating over is r. So that changes your integration. How does r change? It goes from 0 to big R. All right, so pull out all of your constants. So you have 2 pi rho and the thickness T. All of these don't change over your integration. So you're doing 0 to r of r squared times r, so you get r cubed dr. Right,
What
so
is
that,
what is rho again?
oh yeah, rho is always the density.
Thank you.
Yep, density. So that is, think about kilograms per meter cube, right? So density times volume gives you mass, dm. That's what you're looking at, all right? All right, so 2 pi rho t, and then the integral of r cubed is what?
Our
1/4 r to the fourth.
R to the 4 divided by 4, right? Because if you differentiate this, 4 comes down, 4 minus 1, 3, 4 gets canceled, you're left with r cubed, right? So this is changing from 0 to big R, right? So that you're left with 2 pi rho t times r to the 4th divided by 4 minus the second term is 0, right? So I'm not writing that out. 1, 2, right? So the moment of inertia of a disk is 1/2 times pi times rho times t times r to the 4th. Now we can do some simplification here, right? We know that the volume of the disk is equal to what? In terms of the things that are given to me.
1/2 pi r to the fourth.
Nope. What's the volume of a disk?
Pi r
Z-
squared times
pi.
thickness.
That's right. So it's just going to be pi r squared, which is this area, times the height, which is the thickness t. That is equal to your volume V. And we know from the relationship between mass density and volume that the total mass is equal to rho times the volume V, which is equal to rho times pi r squared t. So from this expression, if you take out pi r squared t, if you take out rho pi r squared t, you're left with m. So here you get that Ig is equal to m r, well, you know what? Simplified for you guys. It is rho pi r squared t times r squared over 2. And we know that this is equal to m. So it's just equal to m r squared over 2. Right? So this is the mass moment of inertia of a disk about its center. Next, it's now let's find it about an axis passing through a point P on the edge. So you got your disk, then like that, right? So you have some point P, right? So some point P, and you're trying to find out the moment of inertia about this one. So let's say this one is Z prime, and you know what it is about when it passes through the center about the Z axis, right? How do we do this? That's a question to you guys.
Parallel axis.
Parallel axis. Use parallel axis theorem. So IP is equal to IG plus M R squared. Here the D is just the radius R. So that's equal to M R squared over 2 plus M R squared, which is 3 over 2 M R squared. right, guys, questions, concerns? Can we move on?
What's your double slanted lines there?
Oh, just final answer kind of thing.
Is that what? Okay.
I used to put arrows like this, but then working with vectors and things like that, this can be confusing. So I started doing a double line like that. It's just the final part of what we're looking at.
And those denominators under the mass, is that a 2 or a z?
What do you think?
I think it's a z.
No, it's a 2. It's literally what we found out up top. MR squared over 2. My Z's have a band across, horizontal across them. All right, good. Move on. All right, next is to find, we're going to find IG and IP for a uniform rod of length L and mass M. All right, so drawing it out, we've got the uniform rod like that. It's got its mass center. So there's an axis. That's the axis about which it rotates about its mass center. And then you've got a point P right on the edge. X prime like that, right? And then you've got we're going to distribute it we're going to find a small slither dy, which is at a distance y from the axis passing through the center. All right, so for this case, dm, again, the same thing, density times the differential volume. So that differential volume, because it's a uniform rod, it's going to have a constant cross-sectional area. So let's call that cross-sectional area is big A, right? So I'm going to draw it out, that guy there. Right, times the height of this differential element, which is dy. Right, so from here, my mass moment of inertia, right, that's the formula. That's going to equal rho A, not rho A, it's going to, so R here, because we're taking it from the axis passing through the center, that's just going to be y squared times dm, which is rho A dy. And what does y change from? What are the bounds on the integral?
0 to L over 2.
Nope. You're doing it for the whole rod. You're almost there.
So is it 0 to L?
No, 0 to L would be about that. If you were to do it about, this point here, we're not doing that.
Negative L over 2.
That's right. Negative L over 2 to L over 2. Is that clear, guys? You're going L over 2 down and you're going L over 2 up. Your coordinate frame remains the same. right? So do the same thing, bring the constants out. Rho A minus L over 2 times L over 2 times y squared dy. So what's the integral of y squared?
Y over 3
Right.
to the third.
That's right, y cubed over 3. So minus, and this is going from minus L over 2 to L over 2, right? So you're left with rho A times L cubed divided by 3 times 8. Yep, thank you. 24 plus, well, you know, it's going to be minus, but then you're left with a minus L cubed over 24. So it just becomes plus L cubed over 24. You're left with rho A times L cubed over 12. Next, we do the same simplification, right? Because we know that the total volume of this rod is just going to equal the cross-sectional area A times the length L, right? Therefore, the mass is going to equal rho times that. So it's rho times AL, right? Therefore, your IG is equal to rho AL times L squared over 12. That's M. So you just get ML squared over 12. And this is the rotational inertia about an axis passing through the mass center of a rod. All right, next, for the point P, right? So it's point P over here. What do we do?
Parallel axis.
Parallel axis. So that's that, plus D. What's D now, guys?
Is it Y?
No. For the point P, what is your distance D between the axis that passes through G and the axis passing through P?
L
L
over
over 2.
That's right. So you have L over 2 squared. Right, so that becomes ML squared over 12 plus ML squared over 4. So you get ML squared over 3. All right, good. Questions?
And
Right.
that's this moment of inertia at point P of the rod.
Correct.
Okay.
Moment of inertia for a disk about the center, moment of inertia for the disk about its edge, moment of inertia of a rod about its center, moment of inertia about a rod about its edge.
I had a quick question.
Yes, please.
What would happen if we try to find the moment of inertia at the edge of the circle on the road?
Edge of the circle on the rod. So basically,
Yeah. What would you? Yeah.
about this
No,
axis,
Yes.
same thing as the disk. It'll come out to be a
So
very
do you
similar
combine
thing.
two? Do you combine two of them? Because we.
No, we're not combining the two of them. We're looking at them independently right now because this axis for the rod is for its rotation like this about that, and then for that rotation, right?
Oh, okay, okay.
Whereas for the disk, you're looking, do I have a disk? I don't have a disk, but a cylinder will do. So imagine this is your disk with a very large T, right? So for the disk, one about the center is that one, and then about the edge is that one. All right, does that make sense?
Yes, it does. Thank you.
Yeah. All right, guys, good to move on to next page. Good, good. Okay, I'm moving. All right, next, like we were looking at the area moments of inertia, you could have composite shapes as well. So what we're going to do is we're going to look at a composite shape. So for composite shape shown below, find IG about x-axis. And also find the radius of gyration. Right, so it's basically going to be a rod and a disc. So we're setting it up. So the slender rod has a mass of 10 kilograms and a length of, how much is the length? 1 meter. And the disc has a radius of 0.3 meters and a mass of 6 kilograms. All right, so if I draw it out, so we've got, right, so we've got rod, and then right at the bottom of a rod, we've got a disc. All right, so this is front. If we look at the side, that's kind of a side view. All right, and the x-axis is, let's say that the centroid or this mass center for this composite mass at some point G like that. So this is the x-axis. It's basically, when you're looking at the front view, it's coming out of the page, right? So if this is my composite shape, right, the rod and the disc, the x-axis is coming out of the plane that contains the disc. All right. Okay, so what we can do is, for this composite shape, we can find out where the point G1 is. That's going to be for the rod. We know where the point G2 is, that's the mass center of the disk, right? So let's do some, so let's do some draw the datum, right? So the datum reference point is through the pin at which the rod is connected, right? And let's say that the distance to the point G1, which is the mass center of the rod, let's say that that is y bar 1. Let's say the distance from the top to the mass center, which we have to find out. Let's say that that is y bar, and then let's say that this distance here is going to be y2. All right, so what's the first thing we need to do? So the approach for the composite structure that we're going to use is we will find out where the mass center G is for the structure. Then we will use the parallel axis theorem to find out the rotational moment of inertia about that point for the rod, and then about that point for the disk. And then we'll just add them up. All right, so with that in mind, what's the first step?
Find y bar.
Correct.
Is-
So must find G, right? So what is y bar 1 equal to?
1 divided by 2.
Exactly. So that's just going to be 0.5 meters. Because remember, the length of this rod is equal to 1 meter. And then this length here, the radius is 0.3. So this length is 0.6 meter. All right. So y bar 1 is 0.5 meters. What is y bar 2 equal to?
1 plus 0.3.
Correct. Is that clear, guys? It's just 1 plus the radius of this disk, right? From the datum, from our reference line. All right. So now we find out y bar, right? Because that's what we need to do to find out where G is. So that's just the sum of all of your composite masses. So the location of the centroid, the mass center for your composite masses times the mass divided by the sum of all the masses, right? So that's just equal to 0.5 times 1 times 10, sorry. So 0.5. This is what happens when I don't put units. 0.5 meters times 10 kilograms plus 1.3 times 6 kilograms, right? Divided by 10 kilograms plus 6 kilograms, right? So then kilogram, all that stuff cancels. All right. So how much does this come out to be equal to?
Um, 0.8 meters.
Right. I also have 0.8 meters. All right. So now I can find out what my IG for the rod is. Right? We just derived that. That's just 1 over 12 times ml squared. So that's just 10 times 1 squared divided by 12. So that's equal to 0.833. And what's the units of rotational inertia?
is it kilogram meter squared?
Absolutely. Kilogram meter squared. Okay, next, what I need to do is I need to find out this distance d1 to use the parallel axis theorem, and subsequently, I'll also have to find out this distance d2 to use the parallel axis theorem, right? So d1 is just equal to y bar minus y bar 1, which is 0.8 minus 0.5, so you get 0.3 meters, right? Therefore, the moment of inertia of the rod about the point G, which is your mass center for your composite mass, is just equal to Ig1 rod, which we had found, plus the mass of the rod times d1 squared, right? So that's just 0.833 plus the mass of the rod, which is 10 kilograms, right? So 10 times 0.3 squared. How much does that come out to be equal to?
1.733.
1.733 kilogram meter squared. All right, do the same thing. So next step is to find out what Ig2 for your disk is, right? And that we had found out was just m times the mass of the disk. So I'm just going to say disk. I should also specify rod here, times r squared divided by 2, right? So that's just going to equal, the mass is 6 kilograms, and the radius of the disk is told to be 0.3 squared. That divided by 2. And what is that equal to?
0.27.
0.27 kilogram meter squared. All right, so the distance d2 is just going to equal y2 bar minus y bar, right? From what we've drawn out. So you have y2 bar minus y bar. So y2 bar is equal to 1.3, y bar was 0.8. So this comes out to be 0.5 meters. So now you have Ig for the disk, right? That's just going to equal whatever the mass moment of inertia of the disk about its center plus m times the distance d2 squared, right? So that's equal to 0.27 plus mass of the disk is 6 times 0.5 squared. How much does that turn out to be equal to?
$1.77 as well.
Nice. So you get 1.77. What do you say as well? There's 1.733, different.
Oh yeah, my bad.
Kilogram meter squared. All right, therefore, the mass moment of inertia of your composite body is just equal to the moment of inertia about that same point of your rod plus the moment of inertia about that same point for the disk, which is equal to 1.77 plus 1.733, which is equal to 3.503 kilogram meter squared. All right, so that has to do with the mass moments of inertia. Any questions, guys? If not, let's get into Newton's second law. Good to move on to the next page?
Yes.
Okay. All right, so guys, let's put our statics hats on for a second, right? So remember, rigid body equilibrium, right? So looking at that, I have y-axis, x-axis, and the z-axis just coming out of the page, right? When you're looking at rigid body equilibrium in statics for your body, what's the first thing that we do?
Find what's in equilibrium.
Yeah, but what do we draw?
Oh, FBD.
That's right. The first thing that we do is draw the free body diagram, right? So let's say there's a bunch of forces acting on the body, right? So 1, F2, 3, F4, right? Let's also say there's a bunch of moments acting on the body, M1, M2, so on and so forth. And let's define a random point P within the body, right? So from static equilibrium, from rigid body equilibrium, so rigid body equilibrium is the same thing as static equilibrium, right? And we've done this when you looked at statics, right? What's the sum of all forces equal to?
MA.
No, 0.
Oh.
Static equilibrium, right? And then all the moments above the point P, right? Remember, the moments above the point P is the sum of all the physical moments that act on the body plus the moments that are created due to the forces above the point P, right? You have to consider all moments. And that's equal to 0. All right? Is that clear, guys? Remember that? Just remember that you always have to find out the moments due to the forces as well. All right? Okay, now we get into our stuff, which is general equations of motion for planar motion. Right, so same thing. So we have the free body diagram, right? So you have a bunch of forces, say F1, F2, F3, F4, so on and so forth, right? And you've got moments, let's say M1, M2, and again, you've got a point P. So what do we equate it for dynamics? What do we equate this to?
MA.
That's right. But what's the diagram called?
Kinetic diagram.
Kinetic diagram. KD. Right? And because in our class we're looking at planar motion, we're just going to break the equations down, all right, into the axis. So basically, remember the fact we're always looking at y and x like that, right? So what you're going to end up having is you'll have a resultant motion in the x direction. So that'll be mass times whatever the acceleration of your mass center is in the x direction, right? Plus you'll have a mass times the acceleration component, the translation acceleration of your mass center in the y direction. Plus, and this is what we've been leading up to, you will have this term called, not called, but defined as being equal to your rotational inertia, Ig, times your angular acceleration. All right. And similarly, for this point P, right, let's say that its distance from the y-axis is dx, and from the x-axis it's dy. Right? So looking at the resultant equations of motion that you get, you will get, and these are scalar equations, all right? So you will get sum of forces in the x direction. That's equal to m times your translation of your mass center in the x direction, so the translational acceleration. Right? You'll have sum of forces in the y direction. It's equal to mass times ag in the y direction. And remember, when you're taking moments, you've got to take moments about an axis. And remember, for planar motion, we're just looking at stuff that's happening in plane. The axis is always going to be coming out or going into, depending on how you define it, off the plane that you're looking at, right? So you have moment about the random point P, right? That's going to equal the sum of all of the moments that act on the body plus the moment of all of the forces that act on the body, the moments of all of the forces that act on the body about the point P, right? That is going to equal Ig alpha, and we're defining it to be positive because we're taking that direction to be positive, right? So you have Ig alpha plus, in your kinetic diagram, you also have to consider the moments due to the resultant motion that happens. So you will have moments due to these resultant MA forces, so to speak, right above this point P. So here you'll get, all right, I shouldn't say positive or negative. So we're saying that that direction is positive. So magx times dy, that's going to be positive, so plus magx times dy, and then magy dx about p is going to be negative, right? Because the thumb points into the page, so you get minus magy times dx. So these are your resultant equations of motion about the point for your body, right? You have two translational equations and you get one moment equation about the point. But you can make your life potentially easy if you write the moment equation about your mass center. Right? Then you have to worry about, from a free body diagram, the sum of all the moments plus the moments due to all of the forces about the point G. And that is just equal to Ig alpha now, because magx and magy pass through the points G. So you don't need to worry about the resulting moments due to those translations. All right, and the next two problems that we're going to look at, which will set you up for the next homework, we're just looking at pure translation. So for pure translation, what happens is that this IG alpha term is equal to 0. Therefore, sum of all moments is equal to 0. All right, with that, let's look at this problem. But before we look at the problem, are you guys good here? Do you have any questions? No? Good? All right.